Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll look at our first multivariate analysis method called Principal Component Analysis. So Principal Component Analysis is a multivariate technique for understanding variation and for summarizing measurement data possibly through variable reduction. Principal components, or the variables created in PCA, are sometimes used in addition to or in place of the original variables in certain analyses, and we'll see some examples of how to use and how sometimes principal components are misused in a series of examples. So imagine we have P features. Let's assume that they're continuous variables, and we're treating them all as response variables together in an analysis. So what Principal Component Analysis does, or PCA, is it centers a new coordinate axis to the mean of all of the variables, and then it applies a rotation of the original coordinate axis to a new set of variables which are defined as linear combinations of the original variables. And those unit length linear combinations look like this: a1 times x1 plus a2 times b2, and so on. So we're taking all of the x variables and we're scaling them by individual coefficients a, and then we're adding all those together. And one feature, just to make the PCA, basically to give it almost a unique property, or at least to give the directions of the PCA a unique property, is we're going to make all the a's, the length, be 1. Right? So you remember Pythagorean's theorem? Nope, that's not it. How about the formula for Euclidean distance? So you take the distance of each dimension and you square them and you add them up, and then you would take the square root. But we're going to force all these a's to have length unit 1. So our principal components have a property of descending variance. The first principal component, which in these notes I call Prin1, but sometimes you'll see it as PC for principal component 1, PC2, and so on, is a linear combination of those x's such that this direction through the data, which we'll see in a moment in an example, has the largest variability among all directions through the data. That is, we're going to see an example in a second. The second principal component has the second most variability, and all the way down to the pth principal component, which has the direction of smallest variation in the data. There's lots of names for principal components. Another name is called singular value combination. It's got several other names. And PCA can be done on either the raw or unstandardized data or on standardized data. And we'll see examples of that. The variances of the principal components are called eigenvalues in a singular value or an eigenvalue decomposition. And the coefficients of the principal components are given as eigenvectors of the sample covariance matrix. If you've taken linear algebra, those will be familiar words to you. If not, they're not critical to know for the sake of our class. When you standardize the data, that is by taking each variable, subtracting the mean of that variable, and dividing by the standard deviation of that variable, you have effectively turned the covariance matrix into a correlation matrix. And so you can perform PCA on the correlation matrix as well. What that does is it eliminates the effect of scale of the variables on the analysis, and we'll see why that is important a little bit later. The ordered principal components are uncorrelated variables. That is, they're orthogonal or perpendicular to each other, and they have progressively less variation. Principal components are often viewed as separate dimensions corresponding to the collection of features, and the variability of each component divided by the total variability of the components is a proportion of the total variation in the data captured by each component. Principal component 1 has the largest proportion of total variation, the second has the next, and so on. If data reduction is your goal, then maybe you only need the first few principal components to capture like 95, 98% of the variability. And the remaining, say 5 or 8 dimensions, however many dimensions you have, maybe only explain roughly 2% of your variability. In which case you can reduce the dimension of your data from, say, 10 dimensions down to 2 or 3 dimensions, while only removing about 2 or 3% of your variability. That simplicity is one commonly used feature from principal components. All right. So we need the unit length constraint of the A vector just to make the maximization well defined, because you could scale all the A's by the same number and get different basically coefficients, but all in the same direction. So sort of a minor point. One of the last comments here is that principal components are unique only up to a change of sign for each coefficient. Here's one example of principal component 1. We've got these coefficients, a positive 0.2, a negative 0.4, a positive 0.4, and a negative 0.8. Sorry, positive 0.8. And this specifies a direction. You could plot this direction, and it'd be hard to plot it actually, but there's a direction in 4-dimensional space which corresponds to this linear combination of these features. And that direction is the same whether all those coefficients have the sign they have or the negative of those coefficients. The point is that sort of the x, right? One way to think of it is imagine the x-axis on a plane. Whether you define that x-axis as plus 1x or as a direction, or negative 1x as a direction, you've specified the same axis. You're just pointing in different directions. So this is a definition of the axis pointing in one direction, and this is the same axis pointing in the other direction. And sometimes we might select to change the sign of all of our coefficients for the sake of interpretability. Let's start with a fairly straightforward example, the temperature data. So the following temperature example includes the mean monthly temperatures in January, basically the winter, and July, the summer, for 64 United States cities. And one feature of this data set is that it is in fixed width format. So this is an aside, but this data, the reason I put it in fixed width format is because some of the words or city names have spaces in them. And so that would be a problem if we chose to use spaces as a delimiter. This Little Rock, Arkansas, would have 4 fields in it, whereas Phoenix, Arizona only has 3 fields. So we need a strategy that keeps Little Rock all together as one string. And there's one way we could do it, of course, is if we used comma separated value, CSV, as a file type, and we put quotes around Little Rock, then that would include the space inside as a single string. And I'm just going to show you another way to do that so you don't have to recode your data in case you get data in this form, or in case you have a reason to write data out in this form. So fixed width format gives you, basically you are defining some number of characters that for each field, and all of your data will be aligned using the same number of characters. In this case, we have got a 14-character name followed by a selecting everything, followed by a 5-character temperature in January, followed by a 5-character temperature in July. The spaces that exist are not an important feature. In fact, you don't need any space delimiter in fixed width format. All the fields can run together. And here's how you define it. So there's a function called read.fwf for fixed width format, and you specify the widths. So 14, 5, and 5, and so it will read exactly what I mentioned up here. Another way to, so one thing that's happening here, as we can see when we look at the structure of the temperature data set, which I've called temp, not to be confused with temporary, but this is for temperature. Look at our variable names, or our city names. Albany, followed by 8 spaces, because it's 14 characters wide. So we don't want all this white space, so there is an argument, strip white. So it will strip the white space from our, from any of our, oh, I think I have one more example up there as well. No, the numeric variables are just fine with the spaces. So the strip white, notice I've got Albany now with no additional spaces in Albuquerque and so on. So I've fixed that trailing white space. White space are spaces and tabs, characters, and line returns. Anything that doesn't print things to the screen is called white space. Great. So here's the first several observations. We've got Little Rock with a space in there, no problem. And I have created an ID variable, just numbering the cities from 1 to the number of cities I've got, number 64. And I'll be using that ID variable for printing a little bit later. Let's start by looking at a plot of the data. On the horizontal axis, we have the January temperature, so that's the winter time temperature, and in the vertical axis we have July temperature, the summertime temperature, and both of these are in degrees Fahrenheit. And you can see an obvious positive correlation here. It makes sense that the average monthly temperature in January for a city, if it was hot in the winter, then it might be also hot in the summertime. So in the upper right, we've got cities like Phoenix, Miami, Houston, New Orleans, Jacksonville. These are all cities on the south edge of the United States. And in the bottom left-hand corner, the cold Januaries and cold Julys, we have Duluth, Bismarck, Minneapolis. These are all in the north, Portland, Maine. These are all in the northern latitudes of the U.S. So that's along this sort of right positive diagonal axis. But what can we say about the other axis? Sort of, what are cities in the bottom right? For example, Sacramento or Portland. Portland is a city that doesn't get that cold in the wintertime, so 38 degrees or so, but in the summertime it also doesn't get very warm. So Portland is a rather temperate city. It doesn't have a lot of variability. So this bottom right-hand corner are cities that don't have a lot of temperature variability over the year. In this upper left-hand corner, and we don't have very many good examples in this data set, Omaha, Des Moines, Kansas maybe, don't get pretty cold in January, but also get pretty hot in July. Maybe Phoenix is a nice example of a city that gets it stays fairly warm in January, but gets super hot in July. So in the bottom right, we basically have cities with low variability over the year, and in the upper left would be high variability over the year. And along this diagonal, we're basically, that's just cities that vary relative to their latitude as you'd expect them to. Let's see, let me find where I was. Don't press page up and down. The function in R for principal components is prin_com. And there's two options. One is to produce the principal components based on the covariance matrix, and the other on the correlation matrix, basically by standardizing, or effectively by z-scoring each column of the data first, and that's specified with core equals true. The default is core equals false for the correlation matrix. Let's take a look at the output for doing this. Prin_com, then we have a formula which specifies which variables from the dataset temp we're going to use in our principal components. There's no left-hand side. We just start with tilde, and then we add the variables that we want to include. I'm putting that into temp.pca for the temperature PCA, and a summary of that tells you the importance of the components. The components are numbered, comp1 and comp2. There's the standard deviation of the component in that direction, and these are defined, as I said before, in descending order in terms of their standard deviation. So we've got 12 and then 3. And the proportion of the total variance explained, so how would you calculate the total variance explained? So standard deviation is the square root of variance. So if you square 12, and if you square 3, and you add them together, that's the total variance. And so 144 roughly, and a little bit more, divided by 144 plus 9 is roughly 94%. And the remaining roughly 5 or 6% is left over. So we could basically reduce this data to one dimension and retain almost 95% of the variability. The second set of output here are the loadings. This tells you what the coefficients are for the principal components. For component 1, the coefficient for January is negative 0.9, and the coefficient for July is negative 0.34. If I page up for a moment to an example like this, oops, I've got the January temperatures as x1 and the July temperatures as x2, and these A1 and A2 for the principal component 1 are those loadings, and then for the second component, they're these coefficients A. So page back down. So these are those loadings. The scores give us the coordinates of each data point on the principal component scale. I should really read my comments. That's exactly the words I was looking for. All right. Principal components is effectively doing a location shift. So you take the original axes, so the 0, 0 of our temperature axes, if I page up for a moment, is way down here to the bottom left, right? And the first thing that we do is we shift the origin from 0, 0 up to the grand mean of the data, which is somewhere in the middle of this data cluster. And then, instead of having a horizontal axis and a vertical axis there, we're going to rotate the axes so that we're going to have one axis that goes along the direction of most variance of the data, and then we'll find another one which is orthogonal or perpendicular to that first axis, which describes the least amount of variance. And those are the axes that are going to be plotted in just 1 second. Here we go. All right. So I show you all this code. I probably shouldn't. This shows basically how I'm doing some complicated plotting, but the point really is just to look at these plots. So I've shifted the origin up to the center, the mean of the data, and then I've rotated the axes so that one is along the most variable direction, and the second is on the least variance direction. and those are called principal component 1 and component 2. Based on, if I page up for a moment, the loadings, we can plot the data on these new axes. So what I've done in this plot is I've just overlaid what the principal components are on the original axes, but let's look at the data on the principal component axes. So here, oh man, I'm being bad with my keys today. There's my plot. All right. The PC scores are the coordinates of the data on the principal component scale. We're going to put component 1 on the x-axis, component 2 on the y-axis, and I'm going to fix the coordinate ratio to make them square, not really that important, and I'm going to highlight the axes, not a big deal. Let me just page down a bit and look at that first plot. Here are the data on those original component scales. And you'll have trouble finding which city is which, in part because I've removed the names and replaced them with the numbers, but even worse because these axes are flipped around. Let's think maybe about observation 10 and 2, those sort of spread out numbers. If I scroll up to the original data, here they are, 10 and 2. So we really want 10 to be basically on the right. That city was it Miami? Miami, and then Phoenix was up here. I'll page back down. So in my mind, I want to rotate these axes to basically bring the principal component 1 axis down and have observation 10 be below and observation 2 be above. And they should be on the right. That way my interpretation of PC1 is as I increase, I'm getting warmer, and as I decrease, I'm getting colder in both summer and winter. And then principal component 2 is telling me something about the difference between the summer and winter temperatures. So I'll page back down again. So here's the original scores, which are just sort of arbitrary. And remember that a minus sign is just a way to flip the axes, but doesn't change the interpretation of the principal components. So we'll see in my second piece of code, I actually plot the negative of the scores, and that's going to flip all the axes. And when we look at that second plot, we see here 10 and 2, where your hands should be when you're driving a car, are in the right spot. Nice. So now I've got an interpretation of principal component 1, which is as it increases, the temperatures increase, and as it decreases, the temperatures decrease. And then principal component 2, the vertical axis, says at the bottom we have the least variability between winter and summer temperatures, and in the top we have the most variability between summer and winter temperatures. Nice interpretations, and in fact we can probably drop that second dimension and retain just principal component 1, horizontal, and that retains almost 95% of the variability of all the data. All right, here is a demonstration of the total variance in number 2. In number 1, not too worried about this. This is just saying that when we plot things in 2 dimensions, that's easy. Higher dimensions are harder. In terms of total variance, recall, if I page up for a moment, we have in the summary the standard deviations, and what I said is that the squares of the standard deviations are variances, and we want to know what the total variance is. So we're going to square 12.3 and 3, and I'll page back down. And here this is another way to do it. I'm just calculating the variance of the January and July temperatures. These are the squares of those standard deviations we saw above. So the square of 12.3 is 137, and this is a covariance matrix. So we have January and July as columns and also as rows. And so on the diagonal, 137, and then here, July by July, we have 26. 26. Does that seem right? Let me page up for a moment. Sorry, I lost track of where I am. This says 3. That's for the components. Aha, that's for the components. Let me page back down. Okay. So I'm looking at January and July. The total variance here is 163. If we look at the variance on of the principal components, yes, 154, 1.54 times 10 to the second is 154. That's the 12 squared. And here's the 9. That's the 3 squared. So the sum of this diagonal is also 163. So we have the same total variance whether we're on the original axes or whether we're on the principal component axes. And the proportion of the variance explained by component 1 is just this number, 154 divided by 163. And that's the roughly 94.4%. So here is the rescaled principal components, or rather the resigned. So the original components had negative signs, and I've decided to flip the signs to make them both positive. And here it doesn't matter too much. We'll talk about how to interpret these coefficients a little bit later, but effectively both of these coefficients have positive signs. So the principal component 1 describes how both January and July vary together, how they both increase and both decrease together, whereas principal component 2 has a negative sign for January and a positive sign for July. So this indicates something about the contrast or the difference, how these change differentially. All right, this is just showing that the eigenvalues and eigenvectors are actually the variance terms and the same coefficients that we got for the principal component analysis. So if you know about eigenvectors and eigenvalues, that one's for you. I think the rest of these I've touched on. There's two plots that might be helpful for us, especially when we have higher dimensions rather than just 2. We have a biplot which shows pairs of components. So here's component 1 and here's component 2 on those axes, and it actually shows the directions of the original variables in terms of these principal component axes. This can get pretty confusing when we have lots of dimensions. We'll see an example of that a little bit later. We have the observation numbers plotted. For example, we remember our values 10 and 2, and they're plotted on the original scale of the components, so they're over to the left instead of over to the right where we want them. On the right, we have something called a scree plot. Geologists will know scree as if you've got a cliff, like on the side of a mountain, you'll have the sharp drop off. So this represents sort of a plateau and then a steep cliff that falls down. And then the scree is the rubble at the bottom that tends to just trail off, sort of like a right skew distribution. So if we had several components, often what we would find is we have a couple components that are really important and then lots of components that are fairly trivial. In this case, our scree is just the second component, and component 1 is the one component that's important to us. This plot, the scree plot, will be used to help us judge, if we want to do dimension reduction, how many components should we retain. And basically you want to retain all the ones that have fairly large variance, and you are maybe comfortable excluding the ones that have very little variance. So a quick same example, but using standardized data before doing the principal components. That is, standardizing the data by taking each observation, subtracting the mean, and dividing by the standard deviation for each variable. What that does is it performs the principal component analysis on the correlation matrix instead of the covariance matrix. And when this is important because the scale of the variables will make an impact on what the principal components are on the raw data. For example, if you measure the height of a person in meters as one variable, that has the data on a certain scale. But if you were to measure in centimeters instead, you'd get the same measurements in terms of your data. However, the variability has increased by a factor of 10,000 because centimeters are 100 times bigger than meters, and the variance is a square of the original units. So we've suddenly made the variance of the height measurement much larger, and that variance, that particular variable then is likely to account for a large portion of the variance in our data. So we often want to be insensitive to which units our data are in, and one way to do that is to z-score our data first, and then every variable has equal weight in the analysis. So to show this explicitly, let's start with our data. I'm going to put our original temperature data into a data frame called temp.z for z-scores, and I'm going to show you how to z-score data. One way is manually to do it. So we have a column January. We're taking all the observations, we're subtracting the mean of that column, and then we're dividing by the standard deviation of that column. And I'm going to overwrite our original data to reassign that to January. Another way to do that is through the function scale, and scale by default does z-scoring. So it does exactly this process here. There's other ways to scale data, and there's some options in that function if you want to do it. One advantage to using the scale function is if you look at the structure of the data. In fact, that's what I've done down here. Notice that the July data is scaled to have zero mean. Right? It's hard to see here, but these numbers are not temperatures that for July that we know of. But we also have these attributes. We said that we've scaled it by the center of 75 degrees for July. That's the average temperature over all these cities. And the scale that we used is 5.12. That was the standard deviation of the city temperatures in July. It's nice because this tells us explicitly what that transformation was in the structure. Here is our new data set that's z-scored for January and July. If you calculate the mean for each column using the function call means, here are the means for January and July. And this is times 10 to the negative 16 or 10 times 10 to the negative 15. These are basically 0. These are 0 to, this is basically just a numerical accuracy issue. If we look at the variance of our new z-scored data frame, we see that the variance along the diagonal is 1. That's what z-scoring does. Furthermore, the off-diagonal, 0.7, is actually the correlation between January and July. If you calculate the correlation, you see we have exactly the same thing as the covariance matrix. So z-scoring made the covariance matrix the correlation matrix. So here I'm plotting the original data, but on the z-scored axes. And one thing I've done here is I've made these axes nice and square, and that's because I've z-scored both axes have a 0 as the mean. You can see the 0, 0 point is right where all of these, the big X intersects. And so unit intervals here each represent standard deviation intervals. So one unit is one standard deviation. And because, so that's how I've plotted the data. And you can see that this has a slightly different shape than we had originally on the original scale. Let's do principal components now. So we'll do principal components. I'll zoom back in. And now our standard deviations for component 1 is 1.3, and for component 2 is a little bit less than 1/2. So 1.3 is along this principal component positive sloped line, and then the lesser is along the negatively sloped line. The loadings, 0.7, 0.7, these are, okay, those are the directions. And we just happen to get positives in this case. We don't have to flip the sign this time. And if we look at the, oh, there's one more thing I wanted to show. The proportion of variance explained for each component is now 1/2. And I think that's a general result. It will basically, the proportion of variance explained for each component will basically be 1 divided by the number of components. So 1/2, 1/2. There's one more comment here. There's a row I didn't explain, the cumulative variance. So this is, I'm counting up from component 1, how much variance is explained for component 1, 1/2, and then how much variance is explained for component 1 and component 2, 100%. This is fairly trivial when there's only 2 components, but there's many components. You can look along the cumulative variance and say, okay, after 3 components, I've got 80% of the variance, and then after that, it doesn't increase very much. But ultimately, at the end, you'll have 100% variance. Here's our scree plot again. It looks pretty similar to the on the original scale. However, there are some examples where this would make a huge difference. The reason why we don't have a huge difference here is because both January and July were already measured in degrees Fahrenheit. They were already on the same scale. If for some bizarre reason you measured one in Fahrenheit and you measured the other in Kelvin, or Celsius equivalently in this case because we care about variation, then that would be on different scales. And so one of them would be at 1.8 times the variance of the other. Right? Degrees Fahrenheit is 1.8 more variable than Celsius. All right. I will come back in a second video and we'll focus on interpretation. I think this is a really critical component of principal components. Once you've created them, we're going to use them, and in order to use them, you've got to understand what they mean.